Hello class. I wanted to make this video for you guys since we have a cancellation today due to the snow. Just want to keep everybody up to date and on pace with the things we're going to be learning. So I wanted to make a few quick announcements for you guys. First of all, we will not be having class next Monday due to the holiday. I know I'm sad about it, and I'm sure you guys are as well. But yeah, no class on Monday. As a result, homeworks are usually due on Monday, but instead homework number 1, which I handed out last class, will be due next Wednesday, a week from today, the 18th. Also, lab is going to be starting tomorrow or Friday, depending on which lab section you're in. Lab number 1 is posted on Foxtail, and there's pre-lab questions, which, as the name implies, need to be answered before you come to lab. So make sure to show up to lab with your pre-lab questions answered. One easy way to do that is just download the lab from Foxtail onto your computer. Bring your computer with you and just have the answered questions up on your computer, and I'll check them. They will not be graded. They will only be checked for completion at the start of the lab. And then lastly, just a reminder so you know, the first lab after you guys do it in the next few days will be due next Wednesday at the start of class, and that is turned in online to the Foxtail folder. Okay, cool. So let's pick up where we left off last class. We were talking about scientific notation, just getting some of the basics about measurements down before we move into talking about physics of everyday life. So the next thing I wanted to just introduce or remind you guys of is what are known as metric prefixes. So here we see different metric prefixes. Some of these you're probably familiar with. Centa meaning 100th, like centimeters, represents the scientific notation of 10 to the negative second power. So there's 10 to the negative second power meters in a centimeter, or 0.01 meter in a centimeter. Similarly, you're probably familiar with the metric prefix kilo. So kilo means 1,000, so a kilometer or a kilometer is 1,000 meters. All right, and you see others, mega, giga, tera, and there's more in addition to that. Some of these larger ones you're probably familiar with computing power and memory, gigabytes, terabytes, and so on. And then you see very small numbers are represented with other metric prefixes like milli, micro, nano, and pico. All right, so those are metric prefixes, and you can write a number using the metric prefix rather than the scientific notation times 10 to the power. All right, and I asked you in the homework on that first question to write numbers both using scientific notation and then also with the metric prefix. So what that means, just so you can see an example, we talked last class about the distance to the moon. We were told that it's 384 million meters to the moon. And so we wrote that in scientific notation as being equal to 3.84 times 10 to the 8th power meters. So again, that's one part of what I want in the homework. But I also then ask you to write that same number yet a third way. We see it written two ways here. A third way, which is using the proper metric prefix. So if we looked back at the previous slide, we would see there's no prefix for 10 to the 8th power, right? The closest is giga, which is 10 to the 9th power. So what we'd have to do is we'd have to rewrite this number with the 10 to the 9th power so we could use the proper metric prefix. So rewriting this, we'd move the decimal one more place, and it would be in what I would call improper scientific notation as 0.384 times 10 to the 9th power meters, which now can be written. You replace the entire 10 to the 9th power here with the metric prefix giga, and so you could write this as being equal to 0.384 gigameters. All right, so that's that one. One more example, the length of the pox virus, we were told is 0.0000003 centimeters. Hopefully I said the right number of zeros there. So in scientific notation, we can observe this is 3 times 10 to the negative 7th centimeters. But the tricky thing here, centa is already a metric prefix, right? So again, before we can use a different metric prefix, you can't have like microcentimeters, you can't have two metric prefixes. We need to change it to meters. So to go from centimeters to meters, again, it's 10 to the negative second is centimeters, so we have to combine that with 10 to the negative 7th that we have here, and so 3 times 10 to the negative 7th centimeters is the same as 3 times 10 to the negative 9th meters. In negative 9th, if we looked back at that table or looked it up online, totally fine as well, you would find that the metric prefix to represent times 10 to the negative 9th is nano. And so what the length of the pox virus is approximately 3 nanometers. All right, so that's practicing scientific notation and metric prefixes as you'll be doing on the homework. Cool. All right, that's fun. So the next thing I want to talk a little bit about is unit conversions. All right, so there's times when you're dealing with units where you need to use unit conversions. Otherwise, you might get yourself in trouble. For example, just kind of a quick, easy example to think about. Imagine you were driving down the road at, say, 50 miles an hour, and you do that for 10 minutes. And I ask you, how far have you gone? Well, your default might be, oh, well, let's see, I've gone 50 miles per hour for 10 minutes. Distance equals rate times time. Rate times time, 50 times 10. I went 500 miles in 10 minutes. And that is absolutely false, because your units did not agree. You had miles per hour and you had minutes. So you need to do a unit conversion. Anytime you're dealing with your physics problems or your homework, you need to make sure all of your different physical quantities have the same units. All right, so what we're going to look at today is how to do unit conversions using what's known as a conversion factor. And a conversion factor is basically a relationship that has a value of 1. All right, and so I'll show you some examples of these by doing example problems in the next couple of slides. All right, so here's an example for you. Imagine that you're driving down the road, you see a sign or you see that your car is moving at 65 miles per hour, and you're like, oh, I want to do some of my physics calculations I'm learning about in class, but I always use meters per second. So let's convert your 65 miles per hour that you're driving in your car into meters per second. And to make it easier, I've went ahead and shown you guys on this PowerPoint slide some useful conversion factors. Conversion factors can be looked up online or found in tables in the textbook. So for example, 1 mile is 5,280 feet, the elevation of Colorado or Denver, the mile-high city. You have 1 hour is 3,600 seconds. If you don't remember that one, you can always do 1 hour is 60 minutes and 1 minute is 60 seconds. That's how you come to this relationship. And then lastly, 1 meter is equal to 3.281 feet. So what we do to do this conversion is we have to change hours to seconds as well as miles into meters. All right, so here's what you do. What we're going to do is we're going to take our speed of 65 miles per hour, and all we're going to do is multiply it by 1 2 times. We're going to multiply by 2 conversion factors to start it off, okay? And so we're not actually changing the value, right? Anything multiplied by 1 is still itself, right? 5 times 1 is 5. 10 times 1 is 10. All right, anything multiplied by 1 is still unchanged. So we're going to take 65 miles per hour and start by multiplying it by 5,280 feet per 1 mile. Those two are the same, and therefore we're only multiplying by the value 1. And what you can see, here we have miles on top, here we have miles on bottom. So those units of miles, since you're dividing by it and multiplying by it, those would cancel out algebraically. Boom, red line, cross them out. So we no longer have miles. Now our units are feet and hours. Okay, so to get closer to meters per second, I will now multiply by 1 hour divided by 3,600 seconds in order to convert from hours to seconds. And now our hours, again, we have hours on top and on bottom, so they will cancel. And now we're left with our overall feet per second as our only units. So now what you do with the numbers here is you take 65, you multiply by 5,280 since it's on top, and then you multiply by 1 and you divide by whatever's on bottom. Divide by 1 and divide by 3,600, and what you will find is that's equal to 95 feet per second. Now that's not the end, right? We want meters per second. So I need to do one more conversion, but I was running out of space, so I made it on 2 separate lines. So lastly, we need to convert from feet to meters. So again, notice here, feet is on top. So in order to get it to cancel out, in our conversion factor, we need feet to be on the bottom, which gives us meters on top, which is what we want in our end units. So we know 1 meter is equal to 3.281 feet. So you take 95, multiply it by 1, divide it by 3.281 feet, And boom, look at that, feet cancel out. What are we left with? Meters divided by seconds, or meters per second, the units for speed. And so what we see, taking 95 and dividing it by 3.281, we find that we have 29 meters per second. So if you're moving down the road at 65 miles an hour, you're moving down the road at 29 meters per second. All right, so that's kind of quick. Unit conversion is something some of you may have seen before, but I have another slide here. I want you guys to practice and try this one out. So an average airplane travels around 2,330 kilometers per hour. What is the speed of this airplane in meters per second? So as a reminder, 1 kilometer is equal to 1,000 meters. Go ahead and pause the video and try this one out on your own. Did you pause it? All right, make sure you try it out, and now let's see if you got the answer correct. So here again, we start with what we're given, 2,330 kilometers per hour, and then we multiply it again by 1 2 different times. So we have 2,330 kilometers per hour. We multiply it by 1,000 meters per 1 kilometer. We have kilometers on top. We want to get rid of that. So now we have kilometers on bottom. Boom, those cancel out. Now to get rid of hours and convert it to seconds, we know 1 hour is 3,600 seconds. So we take our 2,330, multiply by 1,000, multiply by 1, divide by 1, divide by 3,600, and what we find is that the airplane is moving at 647 meters per second. Did you get the right answer? I hope so. Cool, good. So that's it as far as what I wanted as far introductory measurement related material. So let's go ahead and jump into chapter 1 of our textbook. Nope, sorry, our hours canceled out. There we go. Okay, now we'll move on to chapter 1. So chapter 1, as I mentioned last class, is about ice skating, and we use ice skating to introduce some of Newton's laws of motion. This will also be part of the theme for lab number 1 starting tomorrow. So the way that the book is set up is it starts with these skating type examples for different day-to-day life, physics of everyday life, topics that we will use as examples of physics. All right, so let's start by thinking about ice skating. I don't know if you guys have ever been ice skating. I have before. Pretty fun. Actually, just this morning with the snow, I was skating, in a sense, down the road in the snow with my dog. So if we think about somebody ice skating, if they're sitting at rest on a flat level surface and you have ice skates on, friction, let's assume, is basically 0. If you start at rest without any push, without pushing off the ground, you're just going to stay there, right? And that's day-to-day life. If you're not moving, you're going to continue to not move. All right, not rocket science just yet. We'll get there later. All right, if you have a push, experience some sort of push, either pushing off with your feet or someone else pushes you, you will begin to move. So you need some outside influence to make yourself start to move. We see that. Once you start moving on your ice skates, you're going to continue to move, right? You don't need any outside forces. Once you get going, if there's no friction, you're going to continue to move in a straight line until you run into the side of the ice rink or crash into somebody else, right? And then if you do, near the edge of the ice rink, you can use your arms and push against the wall to slow yourself down. So there's some relationship between these pushes, what we're going to introduce as forces, and the way we experience motion. Pretty straightforward stuff that we see all the time. So there's 4 questions I want you all to think about for a minute. If you're watching this with a friend, or if you have a roommate nearby just for fun, because physics rules, you can grab them and discuss these with your nearest friend or just your pet. Okay? First question, why does a stationary ice skater remain stationary? What is it about the physical world that makes people not move when they're not being pushed? Why does a moving ice skater continue to move? Why is it that they're going to be able to slide constantly across the surface of the ice? Why do they not come to rest right away? Why does a skater need ice or wheels? If you tried to do the same thing with your tennis shoes on asphalt, you would stop immediately, right? I don't know about you, but sometimes I've tried that, and it even almost happened to me today. I was running down the road and I'd slide on the snow just for fun, but I would hit a patch of
high friction snow where there's a little bit of asphalt underneath and I would catch my feet and almost fall down. All right, luckily I didn't fall down, but I could have. All right, so what is it about ice skates that is different than just moving around with your tennis shoes, and how does a skater stop or start moving? So some of these might be obvious to you, some of them might not be super interesting, but there's actually some really fascinating physics involved in the answers to these questions. So this is sort of just to give you an example of how I will be organizing the different topics that we cover. Each time we'll start with looking at a day-to-day life situation, we'll consider some questions, and then we'll spend the rest of the lecture answering those questions and discussing the physics involved in the answers to those questions. Cool. So let's take it from the top. Why does a stationary skater remain stationary? Well, it's actually part of what's known as Newton's first law of motion that tells us a body at rest is always going to tend to remain at rest. And this idea of things not wanting to move is better known as inertia. So any object with mass has inertia, which means it's going to resist a change to its motion. So if it's at rest, it's going to want to stay at rest. To help visualize this idea of inertia, I'm actually going to show you a quick YouTube clip. So let me flip over to my YouTube video here. All right, so here's a watermelon. It's at rest, and you're going to see in this video clip, as soon as I hit play, somebody's shooting a bullet at it. All right, so watch what happens. This watermelon wants to stay at rest. As it's impacted by the bullet, if you look at that, boom, look, even though it got hit by the bullet, really the watermelon, the center of the watermelon is not changing. It wants to stay at rest. So even as it blows apart, it's actually blowing left and right, both directions at the same time because of its inertia. So even though it got hit from the left side of the watermelon is actually blowing out to the left because of the inertia of the watermelon. And that's just a crazy video. And then here's a guy acting like a samurai who's going to cut a tomato in half with a sword. Watch what happens as he impacts the tomato with his sword. Even though he cuts it right in half and impacts it, look at that. The tomato stays exactly in place because of its inertia. It stays right where it was. And you're welcome to watch other parts of this video. There's some fun stuff related to that. But that is known as inertia, okay? Objects have inertia, and so as a result, they tend to stay at rest. Cool. So that's the answer to the first question. Short answer, inertia. Okay, next one. Why does a moving, clicking ahead. Why does a moving skater continue to move? Well, the actual answer to that, bodies in motion also tend to stay in motion, so the answer is actually inertia. Inertia just means things resist a change in motion. So if they're at rest, they're going to stay at rest. If they're moving, they're going to continue to move. Objects have inertia. So this is what's known as Newton's first law of motion, that an object that is free of any external influence will continue to move in a straight line, covering equal distances in equal amounts of time. Okay, so that means that if its motion is zero motion, then it will stay at zero motion. If it's moving at a constant speed, it will continue to move. And this is really quite revolutionary when Newton realized this, because in day-to-day life, we never really see things that are completely free of external influences, right? Even the ice skater on a skating rink, super smooth ice, eventually, due to air resistance and a tiny bit of friction, will stop when moving. You throw a baseball or roll a ball across the ground, it eventually is going to slow to a stop because of losing energy to air resistance and other things. And so this is really quite revolutionary that Newton realized this. But objects out in space, where there isn't air, do experience this environment where they're basically free of external influences. So things like the moon orbiting the Earth is able to continue to orbit the Earth because there's no external forces acting on it. All right. So that's Newton's first law. Again, it's basically the one-word answer of what is Newton's first law of motion. You would say inertia. More written out, it's an object free of external influences continues to move in a straight line, covering equal distances in equal times. Cool. All right, so next question is, why is it that an ice skater needs wheels why does an ice skater need ice skates / ice? Or if you're talking about somebody using rollerblades or roller skates, why do they need wheels in order to move? All right, and the answer is, as I was kind of implying on the last slide, that in the real world, inertia is hidden by outside forces, primarily friction and air resistance. Okay, so there's outside influences that constantly complicate situations. That's why the ice skater will eventually stop. The ball that you roll across the ground doesn't just roll forever, and so on. All right, so in order to observe inertia thoroughly, we have to work in a situation where we minimize outside influences, working on level ground, using wheels, ice, or air tracks, as I might use in some demonstrations later in the semester. Those sorts of things help us to visualize inertia. Or you can try to have a interaction with an object in a very fast manner, like the guy hitting the tomato with the sword. That happened very quickly, so friction and air resistance weren't able to overwhelm or mask the inertia. All right, so I want to take a time out now that we are understanding inertia a little bit more and talk about some of the physical quantities we're going to be discussing over really almost the entire semester. Okay, so first of all physical quantities, things that we measure, everything from time to length to distance, velocity, force, energy, all of those are different types of quantities, and we're going to discuss the difference between what's known as a scalar and a vector quantity here in just a minute. So the first physical quantity we're going to be dealing with is position. That's an object's location. All right. Velocity is the change in position for an object, so how fast something is moving is the speed, which is related to velocity. Velocity is the change in position with respect to time, so meters per second are the units for velocity. Okay. And so now I want to talk with you a little bit about what's known as a vector quantity. I'll come back to that in a minute, but to introduce vector quantities, I'm going to show you another brief video clip. So I don't know about you, if you've seen Despicable Me, I have, and I quite enjoyed the movie, so I'm going to let none other than Vector himself discuss what a vector is.
Hey! I'm applying for a new film loan, go by the name of Vector. It's a mathematical term, a quantity represented by an arrow with both direction and magnitude. Vector! That's me, because I'm committing crimes with both direction and magnitude. Oh yeah!
That's the response I sometimes get when talking about physics and getting excited, but that's okay. So that's Vector telling us what is a vector? Well, as he just mentioned, it's a physical quantity with both magnitude and direction. So both position and velocity are vector quantities because they have both direction and magnitude. Velocity is not just how fast you're going, it's not just your speed, but also your speed and in what direction you are moving. Same thing with position. It's not just where you're at, how far you've moved, but it's what direction you have moved in, the distance in a given direction, 5 miles due north or 14 meters to the left or so on, right? Same thing with your speed. With velocity, it's not just your speed, not just how fast you're going, but also in what direction you are going. Okay, so we got position and velocity, and so another way to express Newton's first law is an object that is free of external influences moves at a constant velocity. Okay, again, just so you know, that velocity can be equal to 0. All right, so the next physical quantity I want to introduce to you is what's known as a force. So a force is another vector quantity, a push or a pull, something you're probably familiar with. It is a vector quantity because you care about not only the magnitude of the force, the amount of force, but also in what direction that force is acting. And so you'll hear me talk going forward about what's known as the net force. That's the total sum adding up of all different forces on an object. All right, so that's forces. That's an introduction to some of the physical quantities. We're going to talk a little bit more in detail about forces in lab, and we're going to continue from here next class. I feel this video has probably been long enough for you guys on this snow day, so watch it. Let me know what you think, if you have any questions, and be prepared to continue from here next class. Have a great day.